Hello friends, welcome back to the video lecture series on control system. Today we will start with block diagram representation of control system. Introduction. A block diagram is a shorthand pictorial representation of the cause and effect relationship of a system. Look at this block diagram. Here block represent some operation. In this case it is a derivative operation. It has one input signal which is a x and it has output which is a y. The interior of the rectangle representing the block usually contains a description or the name of the element, gain or the symbol for the mathematical operation to be performed on the input to yield the output. So here operation is given which is a derivative operation. The arrow represents the direction of information or signal flow. So here x comes to the block and y is the outgoing from the block. So x is the input for this block and y is the output. So here we can easily say that y is nothing but derivative of x with respect to time t. The operations of addition and subtraction have a special representation. The block becomes a small circle. So this is a small circle called a sum point with the appropriate plus or minus sign associated with arrow entering the circle. So here x and y entering signals to this circle along with its plus and minus sign. So in this case both are plus. So output or outgoing signal is nothing but addition of these two signal, that is x plus y. The output is algebraic sum of the inputs. So in this second case x with plus sign, y with minus sign, so resultant output is x minus y. Any number of inputs may enter a summing point. So here there is nothing like a limitation. We can sum only 2 signals or 3 signals. Any number of signals we can sum and it gives output. So in this case there are 3 signals, x with plus sign, y with plus sign and z with plus sign. So output is x plus y plus z. In order to have the same signal or variable be an input to more than one block or summing point, a takeoff or we can say pick off point is used. So in this case if we want to use this x to 3 different places, then we can take off this x to first, second and third part. So that's why we call the takeoff point. Now we will look at some example. Consider the following equation in which x1, x2, x3 are variables and a1, a2 are the general coefficients. So here given equation is x3 is nothing but a1 x1 plus a2 x2 minus 5. So we can say x3 is combination of 3 parts. First is x1 variable which has coefficient a1, then second is x2 variable which has coefficient is a2, and third is a constant which is nothing but minus 5. So we need to add each and everything. So a1 x1 we can represent, a1 is the gain, so we will just multiply x1 signal with a1, we get a1 x1. Same way a2 x2 we get and minus 5. So all this signal we can represent using summing point. So here a1 x1 with plus sign, a2 x2 with plus sign, but 5 with minus sign. So we get output as x3 is equal to a1 x1 plus a2 x2 minus 5. So this is exercise for homework. You need to draw the block diagrams of the following equations. Here you need to use derivative block, integration block for first example, and for second example you need to use two derivative block for second order derivative. This is very important, canonical form of a feedback control system. So here G is the direct transfer function, or we can say forward transfer function. H is a feedback transfer function. GH is nothing but open loop transfer function, or we can call loop transfer function. Then C by R, this is a control ratio because C is a controlled output and R is a reference input. So C by R is nothing but control ratio, and mathematically we get C by R is equal to G upon 1 plus or minus GH. Now if it is a negative feedback system, then we get G upon 1 plus GH. If it is a positive feedback system, then we get G upon 1 minus GH. So opposite to the sign. Next is E by R ratio, which is nothing but error ratio. So this is an error signal. By comparing reference with controlled output, which is a feedback through H, by comparing these two signal we get error. So error upon R is nothing but error ratio or actuating signal ratio. Mathematically it is 1 upon 1 plus GH. Then B by R ratio. So B is a feedback signal, so primary feedback ratio is nothing but B by R. Mathematically it is nothing but GH upon 1 plus or minus GH. Characteristic equation, very important parameter in a control system. The control ratio is the closed loop transfer function of the system. So this is a control ratio C upon R, which is nothing but G upon 1 plus G plus or minus GH. It depends on negative or positive feedback. The denominator of a closed loop transfer function determines the characteristic equation of system. So here if we put denominator is equal to 0, that equation is nothing but our characteristic equation. So we can say 1 plus or minus g of s h of s is equal to 0. This is the characteristic equation for that system. Now next example, here simple, this is negative sign, so negative feedback loop is given, k upon 1 plus k into s plus 1. So this is the forward gain and 0.1 is the feedback gain. So instead of taking this complicated forward gain, we can assume this is a g of s and 0.1 as a h of s. So we will write each of the parameter in terms of g of s and h of s. Open loop transfer function is, we know, g of s into h of s. Then feed forward transfer function is nothing but g of s. Control ratio is nothing but C by R. So its value is g of s upon 1 plus g of s h of s, because this is a negative feedback system, so sign is opposite over here. Then feedback ratio. So feedback ratio is nothing but g of s h of s upon 1 plus g of s h of s. Error ratio is nothing but 1 upon 1 plus g of s h of s. Closed loop transfer function is nothing but control ratio only. So answer is g of s upon 1 plus g of s h of s. And characteristic equation is nothing but denominator of closed loop transfer function equal to 0. So all these are answer. Substitute g of s h of s in it, we get proper answers. Next is the reduction techniques, which is very important. for block reduction problems. So here two blocks are connected in a cascade. So resultant representation or simplified representation is nothing but G1 into G2. If two blocks are connected in parallel, then we can represent, or simplified block diagram representation is G1 plus or minus G2. Here very important thing is how we can get whether these two blocks are in parallel or in a feedback loop. So for that, just check the signal flow direction. For G1, signal flows from left to right, and for G2 also it flows from left to right. Then we can easily say that these are parallelly connected. Next is feedback loop. So here just look at the flow, signal flow in gain G is is from left to right, but for a feedback it's from right to left. So this is output get feedback with reference input, it gets compared and it gives error signal. So your simplified block is nothing but G upon 1 minus plus GH. It depends on negative or positive feedback. If feedback gain is 1 or unity we can say, then instead of H just put H is equal to 1 and we get G upon 1 minus plus G. Next example is, this is a complicated block diagram representation and we need to reduce this block diagram to canonical form. So step 1 is find whether there is any cascade connection. So of course here G1 and G4 are in cascade. Then step 2 is find whether there are any parallel connection. Of course G2 and G3 are in parallel. So G2 plus G3. Then next there is one feedback loop G1 G4 feedback with H1 and this is a positive feedback. So we get resultant representation is G1 G4 upon 1 minus G1 G4 H1. So G1 G4 feedback with H1, this is positive, so G1 G4 upon 1 minus G1 G4 H1. So these two blocks are in a cascade, so just multiply. So this is a standard canonical form representation. Now we can assume this is a G of S and this is a H of S. Then we can easily find all these parameters. Next is, once again we have to find all these parameters and block diagram is given. So this is very simple example. K1 and this block are in a cascade, so multiply these. Then S with feedback, this is a negative feedback. So easily we get a canonical form. Assume resultant gain as a G of S, then this is H of S, and we know all this formula, just substitute G of S and H of S value, we get all these parameters. So here we solved this problem actually, but this is very easy task. K multiply, then this is a feedback, so we get this is a final answer, canonical form. And these are the values. Next example for homework. So this is also block diagram is given and we have to find all these parameters. So please do this homework because it boosts your confidence. Then few more reduction techniques. Fourth reduction technique is moving a summing point behind a block. So this is a summing point and we want to move to the right side of this block G. So here at this moment both signal get multiplied with G. If we shift over here, then only this signal get multiplied with G, but this downward signal don't have multiplication of G, so we need to add single block of gain G in this path. Moving summing point ahead of block. So here after the G block there is a summing point and we want to shift to the left side of this block. So here downward signal don't have multiplication with G, but if we shift to the left side then it get multiplied, so naturally we have to multiply 1 by G in this path. So 1 by G and G get cancelled and effect of G get eliminated. Moving a pick off point behind a block. So here this signal get multiplied with G, but before multiplication this pick off point is there, so effect of G is not there in this path. But if we shift to the right side of this block, then effect of G get considered, so we have to nullify that, so we need to multiply with 1 by G. Same way over here, summing point pick off point on the right side of block G. So here there is a effect of G in a outgoing signal. If we shift this pick off point to the left side, then effect of G is not present, so we need to add this G block, or we need to multiply G block in this signal. Swap with two neighboring summing points. In these two summing points there is no block or no gain, then we can easily swap these two summing point. So swap means interchange, so this A shifted over here and B get transferred over here along with same signs. Do not change any sign. So to check whether we get all these reduction techniques or rules properly or not, we will go through some examples. Reduce the following block diagram to canonical form. So here first step is check whether any cascade configuration is there or not. So here not a single cascade configuration. Then anything is in parallel, so no, there is nothing is parallel. So what we can do in this block? So here we just move this summing point to the left side of G1 block. So what happen in a H2 means feedback path, effect of G1 is absent, but if we shift it to the left side then effect of G1 is present, so we need to divide this H2 by G1 while shifting to the left side. So we shift to the left side and just multiply by 1 by G1. Next we can do this summing point shifted to the before that G1 and G2 are connected in a cascade, so we just multiply and then we just shift summing point to the left hand side. because there is no gain between these two summing points, so we can swap this summing points. So here we just swap this. Now we can easily get this is a feedback loop and positive along with positive side, so this is a positive feedback loop. So we get G1 G2 upon 1 minus G1 G2 H1. Then these are in a cascade, so we get G1 G2 G3 upon 1 minus G1 G2 H1. And this is once again a feedback loop. This is a negative feedback loop. So this is a standard canonical form. So thank you for watching this video. In the next lecture we will start with lecture 6, that is nothing but block diagram representation of control system part 2.